Hello everyone. If you are aiming to become a Databricks certified data engineering professional, you are in the right place. I have gone through the newly updated official syllabus, summarized the key topics in detail, and compiled a comprehensive study guide to help you approach this exam. Please note that this content represents my own efforts and is not affiliated with my employer in any way. In this video, I will walk you through everything you need from advanced data engineering tasks to best practices so that you are well prepared. Generally, I create my own notes, so I thought why not share my notes here as well, right? So let's get started on the journey to help you become certified.
Databricks Certified Data Engineer Professional Section 1, 20%. Databricks Tooling 1. Explain how Delta Lake uses the transaction log and cloud object storage to guarantee atomicity and durability. Key concepts. Atomicity ensures that a series of changes are performed as a single unit of work. All changes succeed or none are applied. Durability. Once a transaction is committed, its effects persist even in the event of a system failure. How the transaction log works. Transaction log files. Delta Lake maintains a transaction log in a structured, append-only format. The log is stored in the same cloud storage directory as the data. Each commit transaction in Delta Lake creates a new version of the transaction log, represented by a small SYN and/or Parquet file that captures exactly what changed. Append-only, ordered commits. The transaction log is composed of a sequence of atomic commits. Each commit file records data operations such as file additions, file deletions, schema changes, or metadata updates. By reading the logs from oldest to newest, you can reconstruct the entire history of the table. Asset guarantees. 1. Atomic rights. A commit in Delta Lake is an all-or-nothing operation. When a writer finishes a transaction, it writes a new commit file to the log. If the commit file appears atomically using the underlying storage's atomic rename or similar operation, then readers either see the table before the commit or after the commit, never a partial state. 2. Consistency. The transaction log ensures that any snapshot you read is consistent at a given version. All references to data files in the transaction log reflect a consistent state, no partial updates. 3. Durability through cloud storage. Because the transaction log and data files are stored in fault-tolerant cloud object storage, for example, AWS S3, Azure Data Lake Storage, GCS, once a commit is written and acknowledged by the storage system, it is safely persisted. Even if the compute cluster fails, the state of the table is intact and recoverable. Result: by combining an append-only transaction log with atomic commit operations in durable cloud storage, Delta Lake ensures that once a transaction is committed, it's reliably stored, and readers see a consistent view of the table data. 2. Describe how Delta Lake's optimistic concurrency control provides isolation, and which transactions might conflict. Optimistic concurrency control basics. No locks. Instead of locking files during writes, Delta Lake optimistically assumes that multiple writers can operate in parallel without conflicts. Writers proceed with their changes on the assumption that they won't overlap with other ongoing transactions. Isolation level. Delta Lake provides snapshot isolation. Readers get a consistent snapshot of the data as of the latest committed transaction they can see. Writers create new versions of the table atomically, ensuring readers never see partial writes. Validation step on commit. When a writer attempts to commit, Delta Lake reads the transaction log to check if another writer modified the same parts of the table since the writer started. If a conflict is detected, the commit fails, and the writer must retry with a fresh snapshot. Common conflicts. Overlapping data file modifications. If two writers try to modify or rewrite the same data files, for example, same partition of a table, concurrently, this will cause a conflict. For example, one writer might rewrite a partition as part of a compaction job, while another writer tries to insert new data into the same partition. Schema changes. Concurrent schema changes, like adding new columns or changing data types, can conflict if they happen at the same time as other structural modifications. Metadata-heavy operations, changes to partitioning, table properties, or other metadata updates may conflict if two transactions attempt them simultaneously. Result: optimistic concurrency control ensures isolation by allowing concurrent transactions, but validating them at commit time. When a conflict arises, at least one transaction will fail and must be retried, preventing inconsistent states and ensuring correctness without the overhead of locks. 3. Describe basic functionality of Delta Clone. What is Delta Clone? Delta Clone functionality allows you to replicate an existing Delta table to another location or as another table with minimal overhead. This is helpful for tasks like testing, backup, and quickly creating development copies of large tables. Types of clones. 1. Shallow clone copies the metadata of the source Delta table and creates references to the same underlying data files. The new table's data files are not physically duplicated, saving storage and speeding up the clone process. Useful when you want a lightweight virtual copy for testing or temporary analysis. 2. Deep clone physically copies the underlying data files and the transaction log to a new location. Results in a fully independent copy of the table, not affected by changes to the source. Useful for backups, creating archives, or moving data sets to different environments or storage accounts. Basic steps. Use a command like create table mutable shallow clone sourceable or deep clone sourceable to path to destination. After execution, the clone table can be accessed and queried independently. Use cases. Testing. Quickly spin up a shallow clone of production data to run tests without impacting production. Backup and recovery. Create a deep clone to ensure a point-in-time copy that won't be affected by subsequent changes to the source. Data migration. Move data to another environment or cloud storage location by deep cloning it. 4. Apply common Delta Lake indexing optimizations including partitioning, Zorder, Bloom filters, and file sizes key techniques. Partitioning. What it is. Partitioning physically splits data based on the values of specific columns. Why it matters. Queries that filter on the partitioned columns can prune entire directories of data, reducing the amount of data scanned. This leads to lower latency and cost. Best practices. Broken vertical bar. Choose a column with a moderate cardinality. Too few distinct values result in skewed, large partitions. Too many leads to many small files and overhead. Broken vertical bar. Avoid partitioning on columns with extremely high cardinality, like timestamps at full granularity, or extremely low cardinality, like a Boolean. Z-ordering. What it is. Z-ordering uses a multidimensional clustering approach to place related data close together on storage. Why it matters. Improves data locality for queries that filter on multiple columns, reducing input-output by clustering related data. How it works. Broken vertical bar. After writing or updating a table, you run optimize. Zorter by :1, :2 to rearrange data files. Broken vertical bar. This is especially beneficial for columns frequently used in filter predicates. Bloom filters. What it is. A Bloom filter is a probabilistic data structure attached to files, allowing fast checking of whether a file might contain certain values, for example, a given key. Why it matters. Enables more efficient file pruning. If a Bloom filter indicates that a file does not contain values of interest, that file can be skipped. Implementation detail. Bloom filters can be created on certain columns using table properties. For example, broken vertical bar alter table mid-deltatable settable properties. Delta.bloomfilter.enabled equals true. Delta.bloomfilter.columns equals :1. Delta.bloomfilter.max num entries equals 100,000. Broken vertical bar. Be mindful of memory overhead, file sizing and optimize. What it is. Consolidating many small files into fewer larger files of an optimal size, commonly ~1 GB, improves read efficiency and reduces metadata overhead. Why it matters. Too many small files degrade query performance due to overhead in listening and opening files. Using optimize with or without Z-ordering can achieve well-sized, efficient data files. Best practices. Broken vertical bar. After initial writes or incremental updates, periodically run optimize mid-deltatable to coalesce small files. Broken vertical bar. Schedule regular optimize commands, daily or weekly, for frequently updated tables. 5. Implement Delta tables optimized for Databricks SQL service. Key considerations. Use Delta Lake as the storage format. Databricks SQL is designed to run efficiently on Delta tables. Delta's transaction log enables efficient snapshot isolation and incremental scanning. Apply Z-ordering and partitioning for query patterns. Identify frequently queried columns and use Z-order on them for better data clustering. Partition on columns that are often filtered by date or region. For example, a dashboard that frequently slices by date or country benefits from partitioning on these columns. Optimize for by tools and aggregation queries. Pre-aggregate data if query patterns are well known. Storing data at multiple grains or using materialized views, delta live tables or SQL queries that create summary tables can help. Ensure that the table and its files are optimized to reduce scan time and improve dashboard responsiveness. Caching in Databricks SQL endpoint settings. Enable result caching in Databricks SQL for repeated queries. Use Photon Runtime for Databricks SQL endpoints for faster execution and lower costs. Metadata management. Keep table schemas well-defined and stable for consistent performance. Avoid excessive nested structures or frequent schema evolutions, as these can complicate execution plans and statistics collection. 6. Contrast different strategies for partitioning data. For example, identify proper partitioning columns to use. Partitioning strategies. Partition by date time columns. When useful, broken vertical bar your queries predominantly filter on time ranges. For example, where date equals single quote December 5, 2024. Broken vertical bar you have a continuous data ingestion pattern like streaming, where new data arrives daily or hourly. Pros: easy pruning for time-based queries. Well understood pattern. Cons: if granularity is too fine, for example, partition by hour in high-volume tables, you may end up with many small partitions. Partition by low cardinality categorical columns. When useful, broken vertical bar your queries often filter by a small set of categories like country, region, or department. Pros: efficient pruning when filtering by these categories. Cons: if too few distinct categories, you end up with large unbalanced partitions that offer limited pruning benefits. Partition by high cardinality columns. Generally not recommended. When useful, rarely useful. Maybe if the high cardinality column is still commonly filtered on a known subset of values. Cons: large numbers of partitions leading to high metadata overhead and very small files. No partitioning. Rely on Z-ordering. When useful, broken vertical bar when no single column is a good partition candidate. Broken vertical bar when queries are complex and filter on multiple columns. Pros: less overhead in managing partitions. Z-order can still cluster data effectively. Cons: without partitioning, coarse pruning, skipping entire directories, is lost, though Z-ordering partially compensates. Choosing columns to partition by, query frequency and filters. Analyze query logs to find the most commonly filtered columns. Partition by columns that frequently appear in where clauses. Data skew and cardinality. Ensure that the chosen partition column distributes data relatively evenly. For example, country might have a few large countries and many small ones, resulting in uneven partitions. Balance between pruning efficiency and manageability. Too many partitions cause overhead. Too few reduces pruning benefits. Find a middle ground. Pound-sign summary of section. Delta Lake's transaction log and object storage guarantees atomicity and durability by atomically adding new commit files to an append-only log, stored in resilient cloud storage. Optimistic concurrency control provides isolation by allowing concurrent writers and resolving conflicts at commit time. Conflicts occur when transactions modify the same data or metadata. Delta clone functionality enables creation of shallow or deep copies of Delta tables, supporting use cases in testing, backup, and data migration scenarios. Delta Lake indexing optimizations use partitioning, Z-ordering, Bloom filters, and file optimization to reduce scan time and improve query performance. Optimizing for Databricks SQL. Combine these indexing and storage layout strategies with Databricks SQL capabilities. Photon, caching, optimized metadata for low latency, cost-effective analytics. Partitioning strategies. Choose partition columns based on query patterns, cardinality, and the distribution of data. Balance the trade-offs between fine-grained pruning and overhead. In cases where no single column stands out, rely on Z-order to cluster data effectively. Section 2, 30% data processing, batch processing, incremental processing, and optimization. 7. Describe and distinguish partition hints, coalesce, repartition by range, and rebalance background. When processing large data sets, the number and distribution of partitions are critical. The right number of partitions helps in balancing load across the cluster's workers, minimizing data skew, and achieving efficient computation. Spark provides several transformations and hints to adjust partitioning. 1. Coalesce n. What it does, reduces the number of partitions to n without shuffling data if possible. Coalesce tries to minimize the amount of data movement. It often merges existing partitions into fewer partitions. Common use case, after a filtering step that drastically reduces data size, Coalesce helps reduce the partition count to avoid overhead of too many small tasks. Pros, broken vertical bar low cost when reducing partitions. Often avoids a full shuffle. Cons, broken vertical bar data may become skewed if you try to drastically reduce partitions. Since Coalesce doesn't redistribute data evenly, it just merges partitions. 2. Repartition n. What it does, increases or decreases the number of partitions, always involving a full shuffle unless repartition is an op when scaling from the same number of partitions. Common use case, ensuring that data is evenly distributed before expansive operations like joins or aggregations. Pros, broken vertical bar uniformly distributes data. Useful for balancing skew. Cons, broken vertical bar more expensive than Coalesce since it guarantees a shuffle. 3. Repartition by range columns. What it does, partitions the data into n partitions based on the specified columns using range partitioning. This ensures that each partition contains a range of values, which can be helpful when performing operations like sort, merge, joins, or range queries. Common use case, pre-sorting or pre-clustering data according to a certain key or set of keys. For example, partitioning a dataset by a timestamped column to prepare for range-based queries. Pros, broken vertical bar data becomes range partitioned, potentially optimizing downstream operations that rely on sorted or range-based data distribution. Cons, broken vertical bar involves a shuffle, needs careful choice of partitioning columns. 4. Asterisk rebalance. What it does, introduced in newer Spark versions, rebalance redistributes data evenly across the specified number of partitions, ensuring a fair distribution without specifying particular keys. Common use case, after a filter or other transformation, you might have uneven distribution. Rebalance can shuffle data to achieve uniform distribution and avoid skew. Pros, broken vertical bar ensures more evenly distributed data across partitions. Cons, broken vertical bar like repartition, it requires a full shuffle and does not provide control over partitioning by key or range. In summary, coalesce, reduce partitions without full shuffle, can lead to skew. Repartition, increase or decrease partitions with a full shuffle, better distribution, more expensive. Repartition by range, create range-based partitioning, good for sorted or ordered workloads. Rebalance, evenly distribute data across partitions without specifying columns, useful for quickly balancing skew. 8. Contrast different strategies for partitioning data. For example, identify proper partitioning columns to use. General considerations, as discussed previously, choosing the right partition columns in Delta Lake or when writing out Parquet files is crucial for query performance and scalability. High cardinality columns. Avoid partitioning by columns with extremely high cardinality, as this creates many small partitions. For example, partitioning by a unique ID would generate a huge number of tiny files. Low cardinality columns. Partitioning by columns with very low cardinality, for example, a Boolean flag, can lead to few large partitions, offering limited partition pruning. However, if queries almost always filter by this flag, it can still be beneficial. Time-based partitioning. Often you partition by date or timestamped column, such as date or year month day columns, because most queries tend to filter on time ranges. This enables partition pruning for time-sliced queries and simplifies incremental processing like daily batch loads. Domain-specific columns. If data is frequently queried by region, product category, or department, Consider partitioning by these columns. Ensure that the chosen column doesn't produce severe data skew. Key takeaway: the best partitioning strategy depends on your query patterns, data volume, and schema. Balanced partitioning leads to efficient pruning and reduces the cost of scanning unnecessary data. 9. Articulate how to write PySpark data frames to disk while manually controlling the size of individual part files. Why control file sizes? Large datasets can lead to many small files, which degrade performance due to overhead in the file system's metadata handling. Conversely, too few or very large files may also be suboptimal. The sweet spot for many analytical queries is often in the range of a few hundred megabytes to a gigabyte per file. Techniques to control file size. 1. Adjust the number of output partitions before writing. Use df.repartition n or df.coalesce n to define how many output partitions Spark will have before calling df.write. Since each partition typically becomes one output file for file formats like Parquet, you can control the approximate file size by choosing n. Estimation example: broken vertical bar. If your dataset is ~100 gigabytes total and you want ~100 megabytes files, you need about 1000 files. Thus, repartition your data frame to 1000 partitions before writing. 2. Use the data file format's native options if available. Some formats or Spark configurations allow you to set a target file size. For instance, certain delta optimizations or table properties might help optimize file sizes during compaction. For standard Parquet writes, controlling the number of partitions is the primary approach. 3. Post-processing with optimize delta tables. If writing to a delta table, you can write initially and then run optimize to blend aim to merge small files into fewer, larger files. Optimize can help achieve near ideal file sizes after the initial write. 4. Manually iterating and controlling output. In some special cases, you might use map partitions or custom logic to group data into controlled batches. However, this is advanced and less common. Key takeaway: the simplest approach is to control the data frame's partitions before writing. By carefully choosing the partition count based on total data size and desired file size, you can achieve appropriately sized part files. 10. Articulate multiple strategies for updating 1+ records in a Spark table. Type 1. Context. Type 1 updates refer to overriding or updating existing records in a dimension or table to reflect the current state without preserving historical changes. In a data lake scenario, this often means modifying existing data files, something traditional data lake formats are not well suited for. Delta Lake addresses this challenge by providing ACID transactions and update capabilities. Common strategies. 1. Delta Lake merge operation. What? Use the merge into command to update existing rows and optionally insert new ones if they do not exist. How? Merge into target underscore table as t using source underscore data as s on t.id equals s.id when matched, then update set t.value equals s.value, t.other underscore col equals s.other underscore col when not matched, then insert id value other underscore col values s.id s.value s.other underscore col. Pros: atomic transactional updates to a delta table, maintains ACID guarantees. 2. Overwrite a filtered subset. What? If the update set is small, you can filter out the affected partition or subset of data and rewrite it with new values. How? 1. Read the current data. Filter out records that need updating. 2. Union this filtered out dataset with the updated records. 3. Write the combined dataset back with overwrite mode. Pros: simple to implement for small subsets. Cons: not atomic if not done in delta. Can cause consistency issues if readers are accessing the table mid-update. 3. Upsert via a staging table. What? Write your updates, inserts plus updated rows into a temporary delta table. Then run a merge from this staging table into the target. Pros: decouples the computation logic from the final write. Good for complex transformations before applying updates. 4. Delta clone and replace. What? For smaller tables or non-frequent updates, you can deep clone the table, apply modifications in a separate environment, and then replace pointers. Pros: safe but can be more costly and slow for large tables. Key takeaway: for typical Type 1 updates in a data lakehouse setting, merge into Delta Lake tables is the go-to solution due to its atomicity, simplicity, and performance. 11. Implement common design patterns unlocked by structured streaming and Delta Lake. Key patterns: 1. Change data capture, CDC, and incremental loads. Pattern: use structured streaming to continuously ingest changes, inserts, updates, deletes from a source system and apply them to a Delta table using merge. Benefits: ensures near real-time synchronization between source and target tables. Maintains an always up-to-date Delta Lake table. 2. Multi-hop architectures, bronze right arrow silver right arrow gold. Pattern: organize data ingestion and refinement into layers. Broken vertical bar bronze, raw ingested data append only. Broken vertical bar silver, cleansed, filtered, and conformed data. Broken vertical bar gold, aggregated or feature engineered data for reporting, analytics, milliliters, tools. Delta Lake's ACID transactions and time travel ensure consistent transformations. Structured streaming seamlessly propagates increments from one layer to the next. 3. Stream joins with watermarking. Pattern: join to streaming data sources, for example, logs and reference data with stateful operations. Use watermarks to bound state size and avoid unbounded growth. Benefits: real-time correlation of events while maintaining manageable memory usage. 4. Stream static joins with broadcast or delta lookups. Pattern: ingest streaming data and join with static reference data stored in a delta table. The static data can be read once and cached or broadcast to workers. Benefits: low latency lookups and dimension enrichment of streaming data without repeatedly scanning large reference data sets. 5. Upserts in streaming pipelines. Pattern: structured streaming plus delta merge to continuously handle late arriving records or updated facts. Benefits: ensures correctness and completeness of real-time data pipelines with minimal complexity. 12. Explore and tune state information using stream static joins and Delta Lake stateful operations in streaming. When performing aggregations or joins in a streaming job, Spark stores intermediate results in memory state. State grows with the number of keys kept in memory. Without careful management, this can lead to large memory footprints or slow performance. Tuning strategies. 1. Watermarking and state TTL. What? Watermarking tells Spark to drop state for keys that haven't received new data within a given threshold. Example: stream_df equals stream_df dot with watermark. Event time: 10 minutes. Benefit: limits state size, prevents indefinite growth for old keys. 2. Broadcasting static data. Pattern: for stream static joins, if the static dataset is small enough, broadcast it to all workers. Benefit: lookups become local, no shuffles, and less complex state maintenance. Implementation with Python code. Static_df equals spark.read.format delta. Load path to delta. Broadcast_df equals broadcast. Static_df. Joint equals stream_df dot join. Broadcast_df. It result: no large state store needed for this join since broadcast is a simple map-side operation. 3. Delta Lake for point lookups and incremental queries. Pattern: for moderately sized reference datasets, read them periodically from Delta and cache them. If the reference data changes frequently, consider incremental updates. Tuning: optimize the reference delta table through Z-order partitioning to allow fast lookups. If a structured join is performed repeatedly, caching or materializing pre-filtered subsets can reduce state. 4. Reducing granularity of state. If an aggregation or join is done at too granular a key, consider a more coarse-grained key to reduce state size. For example, instead of aggregating per user session event, aggregate at a slightly higher level, for example, per user per day, to reduce the number of keys. 5. State store compression and checkpointing. Spark State Store writes data to disk and supports compression. Ensure you use stable checkpoint locations and consider adjusting compression to improve performance. Periodically review logs and metrics in the Spark IE to understand state growth. 13. Implement stream static joins. What it is. A stream static join involves joining a streaming data frame, unbounded, continuously arriving data with a static data frame, relatively stable and bounded dataset. This is useful for enriching incoming streaming data with reference or dimension data. Key points and best practices. Rating the static data. The static data frame is typically loaded once from a Delta table, or K files, a JDBC source, or other structured storage. Python code. Static_df equals spark.read.format delta. Load /path to dim_table, broadcasting the static data if small enough. If the static dataset is not too large, you can broadcast it to all executors for efficient lookups. From pyspark.sql.functions import broadcast static_df equals broadcast static_df, joining with the stream, assuming stream_df is a streaming data frame. Perform the join as you would a normal data frame. Joined_df equals stream_df dot join. Broadcast_static_df. Key_column. Left. Benefits. The broadcast allows local lookups without shuffling. Your streaming queries can now continuously enrich incoming events with static reference data like product details, user attributes, or lookup tables. Considerations. If the static data changes frequently, you may need to refresh it periodically. This could be done by restarting the stream, or by implementing logic to periodically reload it into a broadcast variable. Though Spark doesn't currently support dynamic broadcast refresh midstream, ensure that the static data is well optimized, for example, using delta with Z ordering or partitioning if needed. 14. Implement necessary logic for deduplication using Spark structured streaming. Why deduplication? Streaming data pipelines often receive duplicate events due to upstream system retrace, network issues, or at least once ingestion semantics. Deduplication ensures you only process unique records once. Key approaches. 1. Stateful deduplication using watermarking pattern. Use a streaming aggregation to keep track of keys seen so far, along with a watermark to remove old keys from state. Example, from pyspark.sql.functions import window # assume stream_df has columns. Key, event time, value # define a watermark on event time to allow state cleanup. Dedupt_df equals stream_df \. With watermark, event time, 10 minutes, \. Drop duplicates, key, event time, explanation. Here, drop duplicates is a structured streaming operation that uses the event time column and a watermark to keep track of which keys have been seen. Once an event is older than the watermark window, its state can be cleared. Pros: broken vertical bar. Simple implementation. Broken vertical bar automatically manages state and cleanup. Cons: broken vertical bar requires a time-based column to use watermarks effectively. 2. Deduplication via Delta Lake merge pattern. If you write the streaming data into a Delta table and maintain an additional unique constraint or a process table, you can use merge to ensure only new records are inserted. Example, SQL code, merge into target_table T using new_data s on T.key equals s.key when not matched, then insert key, event time, value, values, s.key, s.event time, s.value. Explanation, if key is unique, merge will only insert records not previously encountered. This is more batch trigger based than purely streaming stateful deduplication. Considerations. If event time columns are not available, you may need to rely on business keys or merge-based deduplication. Maintaining proper watermarks and ensuring correct windowing logic is crucial to avoid unbounded state growth. 15. Enable CDF on Delta Lake tables and redesign data processing steps to process CDC output instead of incremental feed from normal structured streaming. Read what is CDF. Delta Change Data Feed (CDF) captures row-level changes, inserts, updates, deletes in a Delta table over time. Instead of reading entire datasets and applying incremental filters, you can directly query the changes that occurred since a given version or to misstamp. Enabling CDF table property. When creating or altering a Delta table, enable CDF. SQL code alter table mid-deltatable settable properties. Delta.enable change data feed equals true. Or at creation, SQL code create table mid-deltatable properties. Delta.enable change data feed equals true. Accessing the CDF. Once enabled, you can read changes by querying the table_changes function. Python code changes underscore df equals spark.read.format delta. Option read change feed true backslash. Option starting version 10 backslash. Option ending version 20 backslash. Table mid-deltatable. This gives you a data frame of changes. Insert, update, delete, along with underscore change underscore type and underscore commit underscore version fields. Redesigning data processing with CDF. Old way. Incremental feed. Before CDF, you might have used a starting to timestamp or starting version option on a delta read to pick up incremental changes and then deduce what changed. Inserts versus updates. New way, CDF. With CDF, you directly get the type of change and the relevant rows. Inserts, underscore change underscore type equals insert, deletes, underscore change underscore type equals delete. Updates, represented as a delete followed by an insert of the new row. Processing CDC output, you can now apply business logic that reacts to each change type. For example, you might update downstream tables by applying inserts and updates accordingly. Remove or mark records as deleted in downstream systems when underscore change underscore type equals delete. Continuous processing. Combine CDF with structured streaming by using a batch query in a streaming micro-batch loop. For example, you can repeatedly read new versions of the CDF and apply them to downstream targets. Python code. CDF underscore stream equals spark.readstream. Format delta. Option read change feed true. Option starting version latest underscore checkpointed underscore version. Table mid-deltatable # process CDF underscore stream depending on change types, then write to async benefits of CDF-based approach, eliminates guesswork in determining what changed. More efficient than scanning entire tables or relying solely on timestamp filters. Simplifies data logic by providing explicit inserts, deletes, and updates. Perfect for implementing true CDC pipelines, sensing delta lake changes to downstream system 16. Leverage CDF to easily propagate deletes. What is CDF? Change data feed? The Delta Lake change data feed captures all row-level changes, insert, update, and delete, across versions of a Delta table. Once enabled, you can query the change feed to obtain a record of what changed in each version of the table. How it helps with deletes. Traditional challenge, without CDF. Deleting records downstream, for example, in a dependent system or a gold layer table, is tricky because you only know the current state of the data, not which records got removed. CDF solution. When CDF is enabled, deleted records appear in the feed with underscore change underscore type equals delete. This gives you explicit information about which rows to remove from downstream consumers. Example, Python code, # reading changes from a delta table with CDF enabled changes underscore df equals spark.read.format delta. Option, read change feed, true. Option, starting version, last underscore checkpointed underscore version. Table, mid-deltatable, # filter deletes underscore df equals changes underscore df dot filter underscore change underscore type equals delete. # use deletes underscore df to remove records from a downstream system or reference table. Benefits. Simplicity. No need for complex logic to identify which records disappeared. CDF explicitly records deletions. Consistency. Downstream tables or systems can remain perfectly synchronized with the source as deletions happen. Integrations. Easily propagate these deletes to other stores, caching layers, or search indexes. 17. Demonstrate how proper partitioning of data allows for simple archiving or deletion of data. Partitioning for lifecycle management. Concept. Partitioning a large dataset by a natural dimension, for example, date, can make archiving or deleting older data simpler. Why it matters. Without partitioning, removing old or unneeded data requires filtering and rewriting huge amounts of data. With partitioning, you can often handle these operations at the directory level. Example, partition by date. Suppose your dataset is partitioned by date. For example, year equals 2024 divided by month equals 12 divided by day equals 05. If you need to remove data older than a certain date without partitioning, you would read the entire dataset, filter rows, rewrite it, and remove old data, a costly operation. With partitioning, identify the partition directories that correspond to old dates and remove them directly via a simple directory delete operation or a delta vacuum after dropping partitions. For example, SQL code, alter table mid-deltatable drop partition, date less than single quote January 1st, 2023. This operation removes entire directories in one go, making the archival process straightforward. For archiving, you can copy entire partitions from the primary storage to cheaper, long-term storage, for example, a Glacier tier on S3 or a Cooler Blob storage tier by simply copying those directories. Benefits: operational simplicity. Partition-based archiving or deletion can be done without scanning all data. Performance efficiency reduces expensive input-output and shuffle operations. Cost management, easily move or purge cold data, saving on storage and compute costs. 18. Articulate how smalls, tiny files, scanning overhead, over-partitioning, etc. induce performance problems into Spark queries. What are smalls? Smalls refer to the proliferation of tiny files and excessive partitioning that leads to a large number of small data chunks rather than a few optimally sized files. This is commonly caused by continuous ingestion, for example, micro batches every few seconds that writes many small files, or by choosing partition columns with high cardinality resulting in thousands of small directories. Why are they a problem? 1. File listing overhead. Each Spark job starts by listing files in the input directories. If there are thousands of small files, Spark spends more time just enumerating them. This overhead increases the job's latency before it even starts processing data. 2. Excessive tasks and shuffle operations. Spark creates one task per partition file chunk. A large number of small files leads to a large number of tasks, increasing task overhead and management complexity. More tasks can mean more shuffles and communication between executors. 3. Wasted CPU and memory resources. Reading small files is less efficient than reading larger files of a few hundred megabytes to a few gigabytes. Executors spend more time on overhead rather than on productive data processing. 4. Over-partitioning problems. Partitioning on a high cardinality column, for example, a unique ID per customer, creates many partitions, each with very few rows. Queries may end up scanning many tiny partitions, leading to poor data locality and excessive input-output. Mitigation strategies. Use Optimize for delta tables. Run Optimize mid-deltatable to merge small files into fewer larger files. Pairing with sorter can also improve locality. Balanced partitioning. Choose partition columns that evenly distribute data and have moderate cardinality. Avoid partitioning on fields that create many tiny partitions. Batch writes. Instead of writing many tiny files per microbatch, consider using trigger once equals true or buffering data before writing to create fewer, larger files. Auto-optimize and auto-compaction. Databricks feature. Enable Databricks auto-optimize features to automatically compact small files as data is written. Result: by controlling file sizes and partitioning strategies, you reduce metadata overhead, lower task counts, improve scan efficiency, and enhance overall query performance. # summary of section. Partition hints. Understanding how coalesce, repartition, range, and rebalance differ helps you tailor data distribution in Spark to improve efficiency and reduce skew. Partitioning strategies for data layout. Properly chosen partition columns greatly influence query performance. Strive for a balance between too many and too few partitions, guided by query patterns and cardinality considerations. Controlling file sizes on write. By adjusting the data frame's number of partitions before writing, you can control output file sizes. This ensures efficient file-based operations later on, minimizing overhead and improving runtime performance. Updating tables. Type 1. Use Delta Lake Merge for atomic, efficient updates. Other strategies like overwriting subsets or using staging tables can work but are less direct. Structured streaming plus Delta Lake patterns, leverage CDC, multi-hop architectures, stream joins with watermarks, and stream static joins with broadcasted data to create robust, low latency, and maintenance-friendly pipelines. Tuning state in stream static joins, manage state size by using watermarks, broadcasting static data, optimizing delta tables for lookups, and adjusting granularity. Monitoring and iterative tuning are key. Stream static joins, easily enrich streaming data using static references. Broadcast the static table for efficiency. The duplication in structured streaming, utilize stateful operations with drop duplicates and watermarking, or use merge on delta tables for type 1 deduplication at the sync stage. Change data feed CDF in Delta Lake. Enable CDF to get explicit change records, simplifying incremental processing. Redesign pipelines to read CDF output directly, drastically reducing complexity and latency in CDC scenarios. Using CDF for deletes, CDF provides explicit delete events, making it easy to propagate deletions downstream and maintain consistency across data pipelines. Proper partitioning for lifecycle management, logical partitioning, for example, by date, simplifies archiving or deleting large segments of data without expensive scans. Direct partition-level operations enable efficient data lifecycle management. Avoiding smalls, many tiny files and over-partitioned data degrade performance due to file listing overhead, excessive tasks, and poor input-output efficiency. Optimizing file sizes and partitioning patterns is critical for fast, cost-effective Spark queries. Section 3, 20% Data Modeling 19. Describe the objective of data transformations during promotion from bronze to silver context. Bronze layer. The bronze layer typically contains raw, ingested data in its native format. Data may be semi-structured or unclean, including duplicates, missing values, or extraneous fields that are not immediately useful. Silver layer. The silver layer represents data that has been refined and conformed. It still shows relatively granular detail but is now cleaned, filtered, and partially standardized. This makes it easier for downstream analysts or data products, like machine learning models, by dashboards, to consume data without dealing with low-level data quality issues. Objectives of transformations. 1. Data quality improvements. Remove invalid or corrupt records. Deduplicate records to avoid double counting or skewed analyses. Apply standardized formats, for example, consistent date-time formats. 2. Schema alignment and conformance. Harmonize schemas from different source systems into a common format. Rename or restructure columns for clarity and consistency. Enrich the data by adding reference data lookups or joining with static dimension tables to produce more meaningful attributes. 3. Data validation and business rules. Filter out records that don't meet business-defined criteria. Apply transformations or calculations that produce standardized metrics or fields used downstream. By the time data reaches the silver layer, it should be cleaner, more consistently formatted, and ready for broader consumption. This simplifies subsequent transformations, silver to gold, and makes data more reliable for analytics and reporting. 20. Discuss how change data feed CDF addresses past difficulties propagating updates and deletes within Lakehouse architecture challenge in a traditional lakehouse. Historically, cloud data lake architectures struggled with propagating deletes and updates. Without proper versioning and asset guarantees, engineers had to rely on full table rewrites, complex merge operations, or custom logic to identify and process changed records. This made maintaining synchronized downstream datasets challenging and error-prone, especially when dealing with CDC change data capture scenarios from upstream databases. How CDF helps. Delta Lake's asset properties. Delta Lake provides a transaction log and asset guarantees, allowing for easy and atomic updates and deletes. Change data feed CDF. Once enabled, CDF captures row-level changes, inserts, updates, deletes made to a delta table. Instead of recomputing which rows changed by comparing entire table snapshots, you can directly query the feed for incremental changes since a given version or to misstamp. Benefits. 1. Explicit deletions and updates. CDF explicitly marks rows that were deleted or updated, simplifying the process of removing or refreshing data in downstream tables. 2. Reduced complexity. Rather than writing custom logic to detect changes, you can select asterisk from table underscore changes to get just the modified rows. 3. Efficiency and scalability. By only reading changed rows rather than the entire dataset, you save on compute and input-output costs, making incremental pipelines more efficient and scalable. CDF eliminates guesswork and heavy overhead in propagating changes. It provides a systematic, low-latency mechanism to keep downstream systems in sync with minimal complexity. 21. Apply Delta Lake Clone to learn how shallow and deep clone interact with source target tables. Delta Lake Clones. The cloning feature in Delta Lake allows you to quickly create copies of Delta tables without manually copying data files. There are two types of clones. 1. Shallow clone. What it does, creates a new Delta table with the same metadata as the source and references the same underlying data files. Implications. Broken vertical bar very fast because it doesn't copy data files. It just creates new metadata pointers. Broken vertical bar the clone table does not become fully independent. Any changes to the data files reflect in both the original and the shallow clone, as they share the same data lineage at the time of cloning. Broken vertical bar useful for testing scenarios, quick experiments, or creating a view-like clone for different environments without extra storage cost. 2. Deep clone. What it does, copies the data files and the transaction log from the source table into a new location, creating a completely separate physical copy. Implications. Broken vertical bar slower and more expensive than a shallow clone since it physically duplicates the data. Broken vertical bar the resulting table is entirely independent of the source. Future changes to the source table do not affect the deep clone. Broken vertical bar useful for backups, archiving, or migrating data to a different environment for compliance or disaster recovery purposes. Example commands: shallow clone SQL code, create table mutable shallow clone sourceable. Deep clone SQL code, create table mutable deep clone sourceable location, path to new location. Usage scenarios: shallow clone, quickly set up a test environment or staging area to experiment with queries without incurring additional storage for data duplication. Deep clone, make a fully independent snapshot of a table for safekeeping, analysis in a separate environment, or to provide a point-in-time backup that won't be altered if the source changes later. 22. Design a multiplex bronze table to avoid common pitfalls when trying to productionalize streaming workloads. What is a multiplex bronze table? A multiplex bronze table is a single, unified landing zone in your data lake where data from multiple distinct sources or event types is ingested. Instead of creating a separate bronze table for each source, you store all raw events together, differentiating them by source identifiers, event types, or metadata columns. This approach can simplify ingestion logic, ensure a consistent schema for metadata, and reduce operational overhead. Common pitfalls in productionizing streaming workloads: schema evolution chaos. Different sources may introduce new fields, optional columns, or variant schemas. Without careful planning, you end up with schema drift, requiring frequent manual schema management. Data skew and tiny files, multiple low-volume sources may result in many small files. Without proper partitioning or compaction strategies, querying these bronze tables becomes inefficient. Complex routing logic. If your ingestion logic is too spread out, different jobs per source, maintenance and scaling become difficult. Best practices for multiplex bronze table design. 1. Uniform metadata columns include columns like source, event underscore type, interest underscore time, interest underscore file, interest underscore date, etc. This metadata helps downstream logic know how to parse and route data. 2. Flexible schema handling. Use a semi-structured column like a body column as string or binary, or SYN column for raw event payloads. Store all known attributes in a structured schema alongside the raw payload. Over time, evolve the schema carefully or store unrecognized fields in a nested struct. 3. Partitioning strategy. Often partition by interest underscore date or a time field to organize data and simplify downstream incremental reads. Avoid over-partitioning by source or event underscore type unless they have large data volumes, as this can lead to too many small files. 4. Versioning and schema evolution. Enable Delta Lake schema evolution and write data in a way that can handle optional new fields without breaking pipelines. Keep a record of source to schema mappings. If a new event underscore type is introduced, ensure your ingestion logic can handle it gracefully. By following these guidelines, the multiplex bronze table becomes a stable, scalable foundation from which multiple downstream consumers can process data without continuously re-engineering ingestion logic. 23. Implement best practices when streaming data from multiplex bronze tables. Once you have a multiplex bronze table, you will set up streaming queries to read from it and route data to the appropriate transformations. Key considerations: incremental consumption. Use structured streaming with a checkpoint location. Each microbatch processes only new data appended since the last checkpoint. Use watermarks if you rely on event time-based windowing or deduplication. Dynamic routing logic. Apply conditional logic in the streaming job to separate different event underscore types or sources. You might have a case statement or conditional filtering to create distinct data frames for different downstream paths. Schema-aware transformations. If certain event underscore types require additional parsing, for example, some fields, apply this logic downstream based on event underscore type filters. For less frequently changing schemas, keep logic modular and tested in separate functions. Managing performance and state. Consider using trigger once equals true or appropriate microbatch intervals. Autoscaling clusters can help handle varying volumes of events across multiple event types. Example pattern: Python code. From pyspark.sql.functions import col. From underscore sin underscore tuple # read streaming from the multiplex bronze table bronze underscore stream equals spark.readstream.format delta. Table multiplex underscore bronze # root data by event underscore type click underscore events equals bronze underscore stream dot filter col event underscore type equals click order underscore events equals bronze underscore stream dot filter col event underscore type equals order # process each stream branch with the logic required for that event underscore type process underscore clicks equals click underscore event dot with column click underscore data from underscore col body click underscore schema process underscore orders equals order underscore event dot with column order underscore data from underscore col body order underscore schema # right to intermediate silver tables or directly to gold depending on pipeline design process underscore clicks dot write a stream dot format delta. Option checkpoint to location. Table silver underscore clicks process underscore orders dot write a stream dot format delta. Option checkpoint to location. Table silver underscore orders. By segregating logic per event type after reading from a single bronze source, you maintain a clean ingestion pipeline and reduce complexity. 24. Apply incremental processing, quality enforcement, and deduplication to process data from bronze to silver. Incremental processing concept. Process only new or updated data since the last run, rather than full batch processing of the entire dataset. How to achieve. Structured streaming inherently processes incrementally. For batch jobs, use Delta's ability to merge or filter by underscore commit underscore to stamp or version to pick up only changed records. Quality enforcement. Validation rules. Check schema conformance in the silver step. If a field must be an integer, cast and handle errors. For example, invalid data goes into a quarantine table. Filter out records that do not meet business rules, for example, negative price for an order. Techniques. Use data quality frameworks like Delta Live Tables expectations or custom Spark checks in the silver transformation. Tag records with a validation underscore status column, allowing downstream consumers to use only valid data. Deduplication. Why the duplicate? Streaming systems, especially event-based, may deliver duplicate events due to retries or at least once semantics. How? For structured streaming, broken vertical bar use watermarking and drop duplicates on key columns and an event time column. Python code example, silver underscore df equals bronze underscore stream / with watermark event underscore time 10 minutes / drop duplicates event underscore id. If you rely on a primary key, broken vertical bar use delta merge in a batch or microbatch trigger to handle duplicates at right time. End-to-end example, Python code example, 1. Read from bronze bronze_stream equals spark.readstream.format delta. Table multiplex_bronze 2. Incremental and dedup logic, silver_ready equals bronze_stream backslash. With watermark interest_time, 1 hour backslash. Drop duplicates, primary_key 3. Quality checks, # example, filter out rows with null critical field silver_clean equals silver_ready dot filter, required_field. Is note no, # add a validation status column silver_clean equals silver_clean dot with column validation_status, when, required_field. Is note no, valid. Otherwise invalid. 4. Write to silver table, silver_clean dot write a stream dot format delta. Option checkpoint location, /path to checkpoint silver. Table, silver_table. After this transformation, the silver table contains well-structured, deduplicated, and validated data, ready for analytics or for promotion to the gold layer. 25. Make informed decisions about how to enforce data quality based on strengths and limitations of various approaches and Delta Lake key methods of data quality enforcement. 1. Schema enforcement. Delta Lake's built-in mechanisms. What it does, Delta Lake enforces schemas at right time. If a column doesn't match the expected data type or required columns are missing, the write fails. Strengths. Broken vertical bar automatic and straightforward. Broken vertical bar prevents accidental schema drift. Limitations. Broken vertical bar doesn't validate business logic or complex rules beyond basic type and column presence checks. Broken vertical bar no direct enforcement of semantics like column A must be greater than column B. 2. Schema evolution. What it does, allows adding new columns or relaxing certain constraints over time. Strengths. Broken vertical bar flexibility to adjust schema as source data evolves. Limitations. Broken vertical bar can introduce complexity if not well managed. Broken vertical bar prevents strict enforcement of expected schema shape if used too liberally. 3. Constraints and check constraints. What it does, Delta Lake supports not null and check constraints to ensure certain columns can't be null or must meet a logical condition. Strengths. Broken vertical bar enforces simple data integrity rules at the storage layer. Broken vertical bar prevents writes that violate those rules, reducing downstream data quality problems. Limitations. Broken vertical bar check constraints are limited to relatively simple Boolean expressions. Broken vertical bar no foreign key constraints or complex relational integrity checks. 4. Delta Live Tables, DLT, expectations or data quality frameworks. What it does, leverages pipeline level logic to define expectations, data quality rules, and either fail, quarantine, or warn on invalid data. Strengths. Broken vertical bar flexible and expressive. Can handle complex rules, for example, order_date must not be in the future. Broken vertical bar can automatically produce quality metrics and alerts. Limitations. Broken vertical bar complexity increases as rules grow. Broken vertical bar requires a pipeline orchestration layer, DLT, rather than just storage level constraints. 5. Application level ETL logic. Custom validations in Spark code. What it does, custom Spark transformations can validate data before writing to Delta. Strengths. Broken vertical bar maximum flexibility. Broken vertical bar can integrate domain-specific logic and external lookups. Limitations. Broken vertical bar less standardized. Logic can be scattered and harder to maintain. Broken vertical bar requires careful testing to ensure coverage of all rules. Informed decision-making. Use built-in constraints for simple, universal rules. When a rule is straightforward, for example, no null values or value must be positive. Use table-level constraints for robust, storage-level enforcement. Use DLT expectations or custom validations for complex rules. When business logic is intricate or depends on external data, rely on pipeline-level validations. Balanced flexibility and control. Strict constraints prevent bad data, but can slow down development. More flexible validations let data flow, but require careful monitoring. 26. Implement tables avoiding issues caused by lack of foreign key constraints challenge. Delta Lake currently does not support foreign key constraints as relational databases do. Ensuring referential integrity. For example, every order must have a valid customer underscore id present in a customer's table, must be handled externally. Strategies. 1. Use surrogate keys and enforced dimensions. Maintain a well-curated dimension table, for example, customers with strict primary key uniqueness via unique constraints or DLT checks. Before writing to a fact table orders, join or validate that customer underscore it exists in customers. 2. Periodic integrity checks. After ingesting new data into a fact table, run a batch job or DLT pipeline that checks for orphaned keys. For example, select asterisk from orders where customer underscore id not in. Select it from customers. If violations are found, quarantine these records or alert the data team. 3. Data modeling considerations. Pre-validate incoming data using ETL logic. For example, during the silver step of your ETL, ensure all foreign key columns actually reference existing keys in the dimension tables. Implement merging logic using merge statements that only insert facts if the reference dimension key is found. 4. Documentation and process controls. Clearly document the business logic that enforces referential integrity. Train data engineers and buy developers to rely on well-established pipelines rather than ad hoc writes. Conclusion. Without native foreign keys, integrity relies on careful ETL design, checks, and possibly DLT expectations. Over time, this leads to consistent data despite the lack of a relational constraint mechanism. 27. Add constraints to Delta Lake tables to prevent bad data from being written. Supported constraints, not null constraints, ensures critical columns are never empty. SQL code. Alter table mutable add constraint non underscore null underscore col check. Col is not null. Check constraints. Ensure values meet certain conditions. For example, age greater than 0. Alter table mutable add constraint valid underscore age check. Age greater than 0. Implementing constraints. Define constraints at table creation. Create table mutable id string not null. Agent. Name string. Bool properties. Delta dot enable that if equals true. Then, alter table mutable add constraint valid underscore age check. Age greater than 0. 1. 2. Maintain strict data ingestion policies. If a write attempts to violate these constraints, Delta Lake throws an error, preventing bad data from being persisted. 3. Evolving constraints over time. If business rules change, you can modify or remove constraints, but be cautious of legacy data that might no longer meet the updated rules. Benefits. Immediate feedback. Writers know instantly if they're attempting to insert invalid data. Downstream simplicity. Enforcing constraints at the table level reduces the complexity in downstream transformations, as certain data assumptions become guaranteed. Limitations. Complex business logic. Very complex rules, for example, cross-column dependencies, may require pipeline-level logic or DLT expectations rather than a simple check. No FK enforcement. Constraints do not provide foreign keys. You must still handle relational integrity via ETL logic. 28. Implement lookup tables and describe the trade-offs for normalized data models. What are lookup tables? Lookup tables store reference or dimension data that other tables, fact tables, or event streams frequently join against to enrich or validate attributes. For instance, a country's lookup table that maps country codes to country names, or a product dimension table that provides product attributes referenced by a sales fact table. When to use lookup tables. Normalization benefit. Storing repeated attributes in a single lookup table reduces data redundancy. Instead of embedding product attributes in every row of a large fact table, you store a product key and join to the product dimension. Easier updates. When product attributes change, for example, product name updates, you update them once in the lookup table rather than in multiple large tables. Trade-offs of normalized data models. Pros. Reduced redundancy, saves storage and improves data consistency, as changes propagate from a single source. Data integrity ensures attributes remain consistent across many records. Cons. Join overhead. Every time you query the fact table, you often need to join with the dimension for enriched attributes, increasing query complexity and potentially latency. Complexity in streaming. For streaming pipelines, repeatedly joining a high-volume stream with a static lookup can add overhead if the lookup is large or updated frequently. Denormalization for performance. Sometimes denormalizing, embedding attributes directly into a large table, can speed queries that are join heavy at the cost of storage efficiency. Balancing the trade-offs. Use normalization lookup tables when consistency and ease of maintenance outweigh the cost of joins. Consider partial denormalization if query patterns frequently require immediate access to dimension attributes without joining. For streaming workloads, broadcasting small lookup tables or using caching strategies can mitigate performance costs. 29. Diagram architectures and operations necessary to implement various slowly changing dimension tables using Delta Lake with streaming and batch workloads. What are slowly changing dimensions? SCDS. SCDS capture changes to dimension attributes over time. Instead of merely overwriting old values, you keep track of historical changes for certain SCD types, enabling time travel analyses. Common SCD types. SCD type 0, no changes allowed. Once a record is in the dimension, it never changes. Immutable. SCD type 1, overwrite old values with new values. No history maintained. SCD type 2, keep old values as historical records and add new records for changes, maintaining a full history. Delta Lake architectural considerations, ACID transactions and merge. Delta Lake supports merge operations, which enable atomic upserts and simplify implementing SCD logic. You can conditionally update or insert rows based on whether keys match and whether attributes have changed. Time travel. Delta's version transaction log allows time travel queries, which can help validate SCD operations. Batch versus streaming workloads. Batch SCD pipeline. 1. Periodically run a job that reads the source dimension data. 2. Compare current dimension attributes with existing records in the delta dimension table using a merge. 3. Apply the chosen SCD logic, type 1 or 2, to update or insert records. Streaming SCD pipeline. 1. Ingest incremental changes to dimension attributes as a stream, for example, from a CDC source system. 2. Use a structured streaming for each batch or trigger once equals true approach to apply merge operations to the dimension table. 3. Ensure that your job maintains a checkpoint so that only new changes are processed, making it effectively a continuous SCD maintenance pipeline. Diagramming SCD type 2 example plus group of dashes plus group of dashes plus pipe source db pipe dash 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 greater than pipe bronze ingestion pipe dash 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 greater than row changes plus group of dashes plus group of dashes plus pipe v incremental reads plus group of dashes plus pipe SCD processing pipe spark structured pipe for each batch pipe streaming job pipe merge into delta plus group of dashes plus pipe v plus group of dashes plus pipe delta SCD table pipe with history type 2 pipe plus group of dashes plus. In this architecture, the streaming job continuously reads changes from the bronze layer and applies them to the SCD dimension table using merge. For each updated record, a new version is inserted and the old version is marked as expired. 30. Implement SCD type 0, 1, and 2 tables SCD type 0. Definition. Once written, dimension attributes never change. Implementation. Simply insert the records into the dimension table with no merge logic. If changes occur upstream, you ignore them, or you store them in a new dimension. Type 0 rarely requires complex logic, just a stable snapshot in time. SCD Type 1, definition, overwrite old values with new values, no history preserved. Delta implementation, merge into dim_customer as target using staging_updates as source on target.customer_id equals source.customer_id when matched, then update set target.name equals source.name. Target.address equals source.address when not matched, then insert customer_id, name, address, values, source.customer_id, source.name, source.address. The matched clause updates records in place. Old values are not retained. SCD Type 2. Definition. Preserve full history by adding new rows for changes and marking old rows as expired. Table structure. Add valid underscore from and valid underscore to misstamps or a current underscore flag column. Delta implementation example, merge into dim underscore customer as target using staging underscore updates as source on target dot customer underscore ID equals source dot customer underscore ID and target dot current underscore flag equals true when matched and target dot name less than greater than source dot name then. Close out the old record update set target dot current underscore flag equals false. Target dot valid underscore TO equals current underscore to misstamp when not matched then. Insert new current record insert customer underscore id name address current underscore flag valid underscore from valid underscore to values source dot customer underscore ID source dot name source dot address true current underscore to misstamp null. Logic. If a matching record exists and has changed, mark the old record as current underscore flag equals false and set valid underscore to the current time. Insert a new row as the latest version, current underscore flag equals true, with valid underscore from equals current underscore to misstamp. If no match is found, insert a brand new record. Streaming application of SCDS, use for each batch in your structured streaming query. Python code example, def upsert underscore to underscore scd underscore table, batch underscore df, batch underscore id, batch underscore df dot creatio replace a temp view, staging underscore updates, spark dot sql, merge into dim underscore customer, spark dot readstream dot format, delta, table, bronze underscore updates, write a stream. For each batch, upsert underscore to underscore scd underscore table. Trigger processing time equals 5 minutes. Start. This pattern allows continuous integration of new changes into your SCD dimension. Pound sign summary of section, bronze to silver transformations, aim to clean, standardize, and enrich raw data, making it ready for analytics and further transformation. CDF advantages. Provides a simple, direct mechanism to handle incremental updates and deletes, solving previous complexity and maintaining synchronization across lakehouse layers. Delta clones. Shallow clones offer a quick, storage-efficient way to replicate tables' metadata and references, while deep clones create fully independent datasets suitable for backups, archiving, or isolation. Multiplex bronze table. Centralize raw ingestion for multiple sources into one table with consistent metadata and partitioning. Avoid complexity and manage schema evolution gracefully. Streaming from bronze. Use conditional logic and schema awareness to route data to different transformations. Incremental streaming ensures scalability, while checkpointing prevents reprocessing. Incremental processing, quality, and deduplication. When moving from bronze to silver, incremental reads ensure efficiency. Quality checks filter out invalid data, enforcing data integrity. Deduplication ensures accurate downstream analytics. Data quality enforcement. Leverage a combination of schema enforcement, constraints, DLT expectations, and custom logic. Choose the right approach based on complexity and durability of rules. Foreign key integrity. Without native FK constraints, ensure referential integrity through well-managed dimension tables, periodic checks, and robust EL or DLT logic. Constraints in Delta Lake. Use not null and check constraints to prevent blatantly invalid data from entering your tables, improving overall data quality and trustworthiness. Lookup tables and normalization. Implement lookup tables for consistent attribute definitions and reduced redundancy. Be mindful of join overhead and consider when denormalization might be beneficial. SCD architecture. Use Delta Lake's ACID transactions and merge operations to handle dimension changes over time. Employ time travel and versioning for auditability. SCD types 0, 1, and 2. Type 0, no changes, simplest scenario. Type 1, overwrite existing values, no history retained. Type 2, full history maintained with new rows for changes, enabling time-based analyses. Section 4, 10% security and governance 31. Create dynamic views to perform data masking and 32. Use dynamic views to control access to rows and columns. Dynamic views overview. What are dynamic views? Dynamic views are a powerful feature in Databricks that allow you to define a logical view whose output can vary depending on the context of the user querying the data. For example, you can reference the current user's identity within the view definition and tailor what data they see or how it is presented. This helps implement security and governance policies at the data layer without having to replicate datasets or maintain separate pipelines. Key enablers: current user context. Functions like current_user or current_catalog can be leveraged inside the view definition. Conditional logic in SQL. Use case-when logic, combined with user group membership checks, to mask or filter data dynamically. Integration with Unity Catalog. If available, Unity Catalog provides a centralized governance layer. Dynamic views defined in Unity Catalog can use fine-grained access controls at a global scale. 1. Creating dynamic views for data masking. Data masking modifies sensitive values so that unauthorized users cannot see actual personally identifiable information, or other confidential data, while still allowing authorized users to access it in a controlled manner. Common masking patterns. Replacing sensitive columns with dummy values. For a column like email, you might replace it with a masked version such as xxxxx@masked.com for users who lack permissions. Partial masking. Show only the last 4 characters of a phone number or partially mask a social security number. For example, ********1234. Example, suppose you have a table customers with columns id, email, phone_number, and you want to mask the email column for all users except those in the data_analyst group. Create or replace view masked_customers as select id case when is _member data_analyst, then email else xxxxx@masked.com, and as email case when is _member data_analyst, then phone_number else concat ******** substring phone_number -4, and as phone_number from customers. How this works is _member data_analyst returns true if the current user belongs to the data_analyst group. If true, they see the real email and phone_number. If false, they see masked values. Benefits: centralized control. You manage masking logic in the view definition rather than in the application layer. Dynamic. Different users see different levels of detail from the same view. No data duplication required. 2. Using dynamic views to control row-level access. Row-level security (RLS). You might have a global table, but only want certain users to see rows relevant to their region, department, or role. Example scenario: you have a sales table with columns region, salesperson, amount. You want users in group sales_Europe to see only rows where region equals Europe. Users in group sales_America to see only rows where region equals America. Users not in these groups see no rows. Implementation: create or replace view RLS_sales as select region, salesperson, amount from sales where region equals Europe and is _member sales_Europe or region equals America and is _member sales_America. Result: a user in sales_Europe querying select asterisk from RLS_sales sees only European data. A user in sales_America sees only American data. A user in neither group sees an empty result set. 3. Using dynamic views to control column-level access. Column-level security (CLS). If certain columns are sensitive, like salary or personal details, you can control whether they are visible based on the user's role or group. Example scenario: you have an employees table with columns employee_id, name, department, and salary. Only HR users should see salary. Implementation: create or replace view CLS_employees as select employee_id, name, department, case when is _member our_team, then salary else no, and as salary from employees. Result: HR team members see all columns including salary. Non-HR team members see salary as no. Practical considerations: 1. User and group management. Ensure your Databricks environment, Unity Catalog or Workspace SIM integration correctly assigns users to groups. Dynamic views rely on these group memberships. 2. Performance considerations. Dynamic views add logic to queries. While typically minimal, ensure your conditional logic and functions like as underscore member are used efficiently. 3. Testing and validation. Test views by logging in as different users or using impersonation to verify that access is restricted as intended. 4. Documentation. Document which views apply which masking rules or row-level filters, so that data consumers understand why they see certain data. Pound-sign summary of section. Data masking with dynamic views. Use conditional logic based on user group membership to display masked or partially masked data to unauthorized users, while authorized users see the full values. Row-level access control. Filter rows in the view definition based on the user's group membership, ensuring different groups see only the subset of data relevant to them. Column-level access control. Conditionally return null or masked values for sensitive columns unless the user is in an authorized group. Section 5, 10% monitoring and logging 33. Describe the elements in the Spark AI to aid in performance analysis, application debugging, and tuning of Spark applications. Spark AI Overview. The Spark AI is automatically available for Spark applications run in Databricks or other Spark environments. It provides a graphical representation of your Spark jobs, stages, and tasks, enabling you to inspect job progress, performance bottlenecks, and resource usage patterns. Key elements. Jobs page lists all Spark jobs triggered by an action, for example, a count or a collect. Each job corresponds to one or more Spark stages. Stages page breaks each job into stages, often separated by shuffle boundaries. Useful for debugging, identifying which stage is taking the longest. Understanding shuffle boundaries, where data is redistributed across executors. Tasks page, stage detail, drills down into the tasks for a particular stage. Shows how tasks are distributed across executors, their execution time, input size, and any failures. Useful for debugging. Identify skew. If some tasks run significantly longer, your data might be skewed. Spot executor bottlenecks. If tasks on a certain executor are slow, that executor may be overloaded or experiencing hardware issues. Storage page shows cached RDDS and data frames, their memory usage, and whether they're effectively cached. Useful for performance. Identifying if caching is working as intended and how much memory it consumes. Environment and executors pages. Environment shows Spark configuration, environment variables, class paths. Useful for debugging configuration problems. Executors lists executors, their CPU and memory usage, and task distribution. Useful for resource analysis. Broken vertical bar identify if executors are under or overutilized. Broken vertical bar find executors with frequent GC garbage collection pauses. SQL tab, if using Spark SQL, shows optimized and physical execution plans for SQL queries. Useful for tuning. See how the optimizer transformed the query. Identify expansive operations, for example, large shuffles, scans of massive tables. Overall benefit. By analyzing jobs, stages, tasks, executors, and cache data in the Spark AI, you can pinpoint bottlenecks, imbalances, skewed partitions, and memory pressures, enabling targeted tuning and optimization. 34. Inspect event timelines and metrics for stages and jobs performed on a cluster event timeline views. The Spark AI offers a timeline view or DAG visualization that shows the sequence of jobs and stages, along with their dependencies. DAG visualization displays a directed acyclic graph of RDD/data frame operations. Benefit provides a high-level overview of the job's logical steps and helps identify where shuffles occur. Stage timelines. Each stage can be expanded to see when tasks started and finished, the time spent fetching shuffle data, and task locality levels. Use case. If tasks spend a long time fetching shuffle data, network or data distribution optimizations might be necessary. Metrics. Task level. For each task, you can view metrics such as input size, shuffle read-write size, CPU time, and garbage collection time. Use case. High shuffle read times indicate the need for better partitioning. High GC times suggest increasing executor memory or reducing data spill. By leveraging these timelines and metrics, you can correlate performance issues to specific stages or tasks, guiding efforts like repartitioning, caching, or adjusting cluster sizes. 35. Draw conclusions from information presented in the Spark AI, Ganglia AI, and the Cluster AI to assess performance problems and debug failing applications. Ganglia AI, if available on your cluster, Ganglia or a similar metrics system, provides cluster-wide resource metrics, CPU, memory, network input-output over time. Use case: identify if cluster-wide bottlenecks are causing slow queries. Determine if adding more nodes or upgrading instance types will improve performance. Cluster AI Databricks cluster page shows cluster configuration, autoscaling events, driver and worker node status, and logs. Use case: confirm if the cluster auto-scales properly for peak loads. Check driver logs for exceptions or errors that Spark AI may not detail. Integrating insights. Performance problems. If Spark AI shows tasks stuck waiting on data, and Ganglia shows high network utilization, the bottleneck may be network input-output. If tasks are running slowly and Ganglia shows heavy CPU usage, consider optimizing code or adding more executors. Debugging failures. Use Spark AI to identify failing tasks. Consult executor logs in Cluster AI to see stack traces. If nodes are struggling, as shown in Ganglia, hardware or configuration issues may be at fault. By combining data from Spark AI application level, Ganglia AI cluster level, and the Cluster AI infrastructure level, you can form a comprehensive picture of where performance issues originate and how to address them. 36. Design systems that control for cost and latency SLAs for production streaming jobs. Cost and latency considerations. Right-sizing clusters ought to scale to handle peak loads, but allow scaling down during off-peak times. Consider spot preemptible instances for cost savings if latency requirements are not strict. Efficient data formats and Z-ordering. Use delta tables with Z-order for better data skipping and reduced input-output. Reduce shuffle costs by choosing good partitioning strategies. Latency tuning for streaming. Trigger settings. Use trigger once equals true for batch-like processing or low latency triggers. For example, trigger processing time equals single quote 1 second for near real time. State management. Watermarking to limit state size, ensuring stable memory usage and consistent latency. Consider using efficient checkpointing storage, for example, DBFS or a fast cloud storage tier. Cost control strategies, storage optimization, optimize and vacuum delta tables to maintain efficient file sizes. Monitoring and alerts. Set up alerts on streaming queries, Databricks jobs AI to detect increased processing time, indicating the need to scale or adjust queries. By carefully balancing cluster configuration, data layout, and trigger intervals, you can meet latency SLAs while controlling costs. 37. Deploy and monitor streaming and batch jobs deployment patterns. Databricks jobs. Use the Databricks jobs AI or CLI to schedule notebooks, jars, or Python scripts. Multitask jobs enable complex workflows with dependencies and error handling. CI/CD integration. Store code in Git-based repos and use CI/CD pipelines to deploy job configurations automatically. Test changes in lower environments before promoting to production. Monitoring running jobs. Jobs AI. Inspect job run history, logs, and cluster details. Set up email or Slack alerts for failures or long-running jobs. Structured streaming AI. A separate tab in the Spark AI shows metrics for streaming queries, including input rates, processing times, and state store metrics. Helps identify bottlenecks in streaming pipelines, for example, slow sources, large state, or output sync issues. Batch job monitoring. Use Spark AI for post-run analysis. After a batch job completes, review the Spark AI to see which stages took the longest. Identify opportunities for future optimization. Iterative improvement. Continuously review job performance, adjust cluster sizing, optimize code paths, and ensure that incremental data processing steps adhere to established SLAs. Pound-sign summary of section, Spark AI and metrics, essential for identifying performance bottlenecks at job, stage, and task levels. Ganglia and cluster AIs provide cluster-level insights, helping diagnose resource and scaling issues. Cost and latency optimization in production streaming jobs, balancing resource usage, file formats, and triggers ensures meetings live efficiently. Deployment and monitoring use Databricks jobs, CI/CD pipelines, and alerting to maintain reliable, scalable, and maintainable batch and streaming pipelines. Section 6, 10% testing and deployment 38. Adapt a notebook dependency pattern to use Python file dependencies. What this means. Databricks notebooks often begin as self-contained code units. As projects grow, it's common to modularize code by extracting reusable logic into separate Python files or modules. Instead of relying on %run commands to include code from other notebooks, notebook chaining, you may be expected to transition to a more production-grade approach, using Python file dependencies that are packaged and referenced directly. Key concepts and best practices: modularization, move shared logic, utility functions, transformations, common validations into Python modules that can be version controlled and tested independently. Workspace files and repos. Databricks allows storing Python files directly in repos or the Databricks file system (DBFS). By placing Python files in a well-structured directory, you can import them using standard Python import statements, init scripts, and Python path. If needed, adjust environment variables to ensure that custom modules are discoverable. However, Databricks repos handle path resolution if the code is in the repo root or subdirectories. Testing dependencies locally. Before pushing code to Databricks, test module imports locally or in a development cluster. Confirm that the cluster's runtime environment recognizes the directories as valid Python packages. Version control integration. When using Databricks repos connected to Git, ensure that changes to Python modules are reviewed, tested, and integrated in a CI/CD pipeline. Exam tips. Understand how to restructure code from %run some underscore notebook patterns into from my underscore package import my underscore module patterns. Be familiar with how the directory layout influences imports. Know how to handle common errors such as module note founder and how to adjust file structure. 39. Adapt Python code maintained as wheels to direct imports using relative paths. What this means. Many production-grade Python projects in Databricks are distributed as wheels. WHL files to clusters, enabling a clear separation of environments. In a more flexible development workflow, or for rapid iteration, you may switch from deploying as wheels to working directly with Python source code using relative local imports. Key concepts and best practices: wheels versus local imports. Wheels, precompiled distributions that you install on clusters via the IE or cluster init scripts. They are stable but less flexible for rapid iteration. Local imports import Python code directly from the workspace files. This allows quicker updates without repackaging into a wheel. Package structure for relative imports. To use relative imports from module import function, ensure the codebase is structured as a proper Python package, that is, with _init_underscore__.py files. Moving from wheels to direct imports, remove installation steps for the wheel on the cluster. Place the Python modules directly in the repo directory. Update import statements from something like import mylib, assuming mylib was installed as a wheel, to a relative path, from my_project.my_module import my class. Testing and validation. Test your new import pattern in a development cluster before relying on it in production. Make sure that your modules are on the Python path and that you can run your transformations and tests successfully. Exam tips. Know how to package code into a wheel and how that differs from just using local imports. Understand Python packaging basics, directory structure, __init___.py files to enable relative imports. Be prepared to explain pros and cons of wheels versus direct source imports in a Databricks environment. 40. Repair and rerun failed jobs. What this means. In production scenarios, data pipelines may fail due to transient issues, logic errors, data quality problems, or external system downtime. As a data engineer, you must know how to diagnose and fix the issue, then rerun the failed job. This involves understanding Databricks job run configuration, cluster logs, and the job IE, as well as potentially adjusting the code or configuration. Key concepts and best practices: job monitoring and logging. Use the Databricks jobs IE to review run history, logs, and error messages. The standard output logs, Spark driver and executor logs, and notebook output are crucial for diagnosis. Common failure causes: schema changes in upstream data, missing or corrupted input files, cluster configuration or library installation issues, transient errors in external systems, for example, database downtime, network issues. Repair runs. Databricks allows you to repair a failed run. A repair run can skip tasks that previously succeeded and only rerun tasks that failed or were never completed. This is especially useful in complex multitask jobs. Automated alerts and CI/CD. Implementing alerts and using CI/CD pipelines to test code changes before deployment helps reduce the frequency of failures and speeds up the repair process. Resuming from Delta checkpoints. If your idle pipeline uses Delta Lake features, for example, merge operations, structured streaming with checkpoints, you can often resume a failed job without reprocessing all data. Understanding how stateful operations work is key. Exam tips: be familiar with the Databricks jobs IE and the process of repairing runs. Know how to read Spark job logs and error messages to pinpoint failure causes. Understand the implications of partial runs, how to skip steps already completed successfully, and how to avoid reprocessing large volumes of data unnecessarily. 41. Create jobs based on common use cases and patterns. What this means: in Databricks, a job is a way to schedule and run notebooks, jars, wheels, or Python scripts. Common use cases include orchestrating periodic idle workloads, running batch transformations, scoring models, or performing scheduled data quality checks. Key concepts and best practices: batch idle pipelines. A common pattern involves running a job that 1. Ingests raw data from a source system, for example, cloud storage, databases, message queues. 2. Cleans, transforms, and enriches the data. 3. Writes the output to a Delta table or another data store for downstream consumption. Data quality and validation jobs. Another pattern is having a job that runs a suite of data quality checks before publishing data to production tables. This might use tools like expectations, Delta live tables, or custom Python validation scripts. Machine learning scoring inference jobs. If you have ML models registered in MLflow, a job might 1. Load the trained model. 2. Apply it to new data. 3. Write predictions back to a destination, Delta table or external system. Orchestration and dependencies. Even for single task jobs, you can design them with robust retry logic, logging, and notifications. For example, send an email or Slack message on failure. Exam tips: understand how to create and schedule a simple job in the Databricks IE. Know how to configure clusters for jobs, job clusters versus all-purpose clusters. Be aware of job parameters and how to pass configuration settings like input and output paths into jobs at runtime. 42. Create a multitask job with multiple dependencies. What this means: multitask jobs let you build workflows comprising multiple tasks that can depend on each other's success before running. For example, you may have a job with 3 tasks. 1. Ingest task: load raw files into a bronze table. 2. Transform task: aggregate and clean the bronze data into a silver table. This runs only if the ingest task succeeds. 3. Publish task: update a gold table or external system with enriched data. This runs only after the transform task completes successfully. Key concepts and best practices: creating a multitask job. In the Databricks jobs IE, you can add multiple tasks. Each task can be a notebook, a Python script, a jar, a SQL query, or a Delta live tables pipeline. You then define dependencies between tasks. Defining task dependencies, you specify which tasks must complete successfully before a downstream task starts. This controls the execution order and ensures data is ready before subsequent steps run. Scheduling and alerts. You can schedule the entire workflow to run at a fixed interval or triggered by events. Set up failure notifications so you can quickly identify and repair broken tasks. Retries and failures. Assign appropriate retry policies to tasks that might fail due to transient errors. Consider adding compensating steps or lineage tracking so you can recover gracefully. Advanced patterns. Multitask workflows can incorporate branching logic and fan-out fan-in patterns. For example, run multiple parallel transformations and then combine results. Exam tips. Know how to create multitask jobs in the IE or via the REST API. Understand how to set dependencies, retry policies, and notifications. Be prepared to explain how a multitask job can streamline nettle pipelines compared to multiple separate single-task jobs. 43. Design systems that control for cost and latency slows for production streaming jobs. What this means: for streaming workloads, you need to ensure that data is processed within acceptable latency windows, for example, near real-time data updates, while managing resource usage and cost. This requires careful architectural decisions and configuration tuning. Key concepts and best practices. Cost control strategies, cluster sizing and autoscaling. Use autoscaling clusters that scale up to handle peak loads and scale down during off-peak times. Choose the right cluster type, for example, spot instances or lower-cost instances if appropriate. Delta Engine and Photon. Leverage Databricks runtime optimizations and Photon for lower cost, higher performance queries. Efficient data formats. Use the Delta Lake format with optimized tables and Z-ordering for faster queries. Minimize shuffles and skew to reduce unnecessary computational overhead. Latency considerations. Structured streaming triggers. Set appropriate triggers. For example, trigger once equals true for batch-like processing or shorter micro-batch intervals to meet your latency requirements. Stateful operations and checkpointing. Ensure that stateful transformations, for example, aggregations, joins, are checkpointed efficiently. Optimize checkpoint location. Prefer high throughput, low latency storage, and ensure state is managed to prevent large state store overhead. Concurrency and parallelism. Increase the number of shuffle partitions if the workload is CPU bound, or decrease them if it's causing overhead. Proper parallelism ensures lower latency without excessive cost. Monitoring and tuning. Metrics and observability. Use the Spark IE and Ganglia Prometheus integration to monitor streaming throughput, latency, memory usage, and cluster utilization. Adaptive query execution. AQ. Let Spark handle queued data and optimize joins and aggregations dynamically. Cost alerts and budgets. Integrate with cost management tools, for example, Databricks Cost Analytics, native cloud provider cost tools to monitor spending. Set alerts to trigger if costs exceed thresholds. Exam tips. Understand the trade-offs between low latency and cost. Be familiar with Databricks features like autoscaling, spot instances, and Photon to manage costs effectively. Know how to configure streaming triggers and checkpointing to achieve required SLAs. 44. Configure the Databricks CLI and execute basic commands to interact with the workspace and clusters. What this means: the Databricks CLI command line interface is a utility allowing you to interact with the Databricks environment from your local terminal or within a CI/CD pipeline. You can perform tasks such as managing clusters, jobs, notebooks, and DBFS files without using the Databricks IE. Key concepts and best practices. Installation. Install the CLI using pip install Databricks CLI. Configuration. Run Databricks configure-token to set up authentication. Provide your Databricks host URL, for example, https://less than region greater than azure@databricks.net and a personal access token. Ensure your token has appropriate permissions, for example, job and cluster management roles. Common CLI commands. Workspace commands. Broken vertical bar Databricks workspace ls to list contents of the workspace. Broken vertical bar Databricks workspace import-export to move notebooks between local and remote. DBFS commands. Broken vertical bar Databricks FSLS to list files on DBFS. Broken vertical bar Databricks FSCP to copy files to from DBFS. Cluster commands. Broken vertical bar Databricks clusters list to see available clusters. Broken vertical bar Databricks clusters start-stop to manage cluster lifecycle. Security and credentials. Store credentials securely. For example, environment variables in CI/CD pipelines. Secret managers. Rotate tokens periodically and use service principals or Azure AD credentials where applicable. Exam tips. Understand how to configure the CLI and confirm connectivity. Be able to list workspace and DBFS objects, and know how to start/stop a cluster. Recognize the correct syntax and parameters for commonly used CLI commands. 45. Execute commands from the CLI to deploy and monitor Databricks jobs. What this means: the CLI can be used to create, update, run, and monitor jobs without interacting directly with the Databricks AI. This is particularly useful for automation, CI/CD processes, and scripted deployment flows. Key concepts and best practices. Job deployment via CLI. You can create a job by providing a SYN specification file that describes the job's tasks, clusters, libraries, and other configurations. Databricks jobs create -syn file job _ definition.syn updating jobs. Use Databricks jobs reset -job id less than id greater than -syn file new _ job _ definition.syn to update an existing job's configuration. Running jobs. Trigger a run with Databricks jobs run now -job id less than id greater than. You can pass parameters to the job if it's parameterized. Monitoring jobs. Databricks jobs list to see a list of jobs and their IDs. Databricks runs list to see runs, their statuses, start times, and results. Databricks runs get-run id less than id greater than retrieves detailed output and status of a specific run. Integrating with CI/CD. The CLI commands can be integrated into deployment scripts, for example, in GitHub Actions, Azure DevOps, Jenkins. This enables fully automated provisioning, updating, and monitoring of data pipelines. Exam tips. Know how to create a job with a SYN spec. Understand how to trigger and monitor a job run. Be comfortable with reading runs get output to understand if a job succeeded or failed. 46. Use REST API to clone a job, trigger a run, and export the run output. What this means: Databricks offers a comprehensive REST API that can manage virtually all aspects of the platform. For certain tasks, like cloning an existing job, triggering runs programmatically, or retrieving run results, the REST API can be leveraged directly. This may be part of advanced automation use cases or integrating Databricks into a broader ecosystem of tools. Key concepts and best practices. Authentication and headers. Use a personal access token, PAT, or OAuth tokens in API calls. Include authorization, bearer less than token greater than and content type. Applications and headers. Common job-related endpoints. Clone a job. Post/API/2.1/jobs/create can be used with the configuration of an existing job to clone it. You essentially take the SYN of the existing job retrieved by /API/2.1/jobs/get job _ID equals less than job _id greater than and submit it as the payload to create a new, similar job. Trigger a run. Post/API/2.1/jobs/run now with a SYN payload specifying job _id and any parameters will start a new run. Exporting run results. Broken vertical bar. Use get/API/2.1/jobs/run/get run _ID equals less than run _id greater than to retrieve run metadata, including the state, success, failed, etc. Broken vertical bar. If your job run produced notebook output, you can retrieve it using get/API/2.0/workspace/export with the notebook path. Or if the run includes run _id, get/API/2.1/jobs/run/get-output, run _ID equals less than run _id greater than can be used to get the textual output of the run. For example, if it was a notebook job. Automation and tooling. Use tools like curl or Python's requests library to issue REST calls. Combine API calls with shell scripts or Python scripts to automate cloning, running, and retrieving results. Error handling. Check for non-2xx response codes and handle errors. For example, insufficient permissions, malformed SYN. Use detailed error messages from the API response to debug issues. Exam tips. Understand how to authenticate and send a REST request to Databricks. Know the base URL and token setup. Know the key endpoints and request payload structures to clone a job or trigger a run. Be aware of how to retrieve run outputs and logs via the API. Pound-sign summary of section. For the testing and deployment section, focus on understanding how to structure your Databricks projects for modularity, reusability, and maintainability. This includes moving from notebook chaining to Python module imports, handling package distribution and imports, both as wheels and via local paths, and operationalizing your code in production by diagnosing issues, repairing runs, and ensuring robust and testable pipelines. Jobs and workflows. Know how to create simple and complex jobs, manage dependencies, and understand patterns for common use cases. Multitask pipelines. Be ready to construct multi-step idle pipelines within a single job, ensuring dependencies and tasks flow correctly. Cost and latency in streaming. Demonstrate awareness of architectural decisions, configuration settings, and Databricks CLI. Familiarize yourself with installing, configuring, and using the CLI to manage clusters, workspaces, files, and jobs. Job deployment and monitoring via CLI. Understand how to deploy new jobs, modify existing ones, trigger runs, and check statuses using CLI commands for integration into automated workflows. REST API operations. Know how to authenticate with tokens, call endpoints to clone jobs, trigger runs, and retrieve outputs. This includes understanding some payload structures, endpoints, and response handling.
As you wrap up your studies, remember that practice makes perfect. If you found this guide helpful, please share it and don't hesitate to let me know if you would like to see more content like this for other certifications. I have no plans for monetizing this channel, even in the future. I do it simply to help others, but hearing your feedback genuinely motivates me to keep going. Good luck on your journey to become a certified professional. Thank you.